Hello, everyone. Thank you for taking the time to listen to my talk. My name is Chris Harris, and I'm currently working towards my master's in GIS from Penn State University. And today I'm going to talk about the different exploratory spatial analyses that I performed in order to identify potential wildlife crossing structure locations in the Paradise Valley of Montana. Here's a general outline for my talk. I'll be giving a brief background on the issue of wildlife vehicle collisions before talking about my specific study area. I'll outline the methods that I use to answer my research questions, which involve classifying aerial imagery. And finally, I'll present the locations that I've deemed appropriate for wildlife crossing structures. So I'll start by painting a broad ecological picture for you. Over the past several decades, wildlife in the Western United States have experienced habitat fragmentation due to human development. Simply put, we've built our homes and roads in areas where wildlife historically lived and found their food. And this has led to a greater overlap of humans and wildlife. This is just a simple example of a progression of a small subdivision south of Missoula, the town where I grew up in Western Montana. Ultimately, the increased overlap of humans and wildlife has led to an increase in wildlife vehicle collisions. And the picture here illustrates the danger that wildlife can face when crossing our highways. Of particular concern are ungulates like elk, whose large body size can cause serious vehicular damage and also bodily injury to motorists. Here's an example of a vehicle that struck an elk on one of Western Montana's highways and rolled due to the impact. The driver of the vehicle luckily escaped alive, but this is a great example of the danger these animals pose. Over the past couple of decades, the Montana Department of Fish, Wildlife, and Parks, as well as the Montana Department of Transportation, have acknowledged the danger that wildlife vehicle collisions pose to motorists, and they've installed a variety of different wildlife crossing structures to mitigate these collisions. This particular structure was built across US Highway 93, and it's located on Confederated Salish and Cootee tribes land. Before a crossing structure is placed, we should understand how animals are moving through their habitat and when and where they decide to cross our highways. This ensures that when we place a structure somewhere, wildlife will actually use it. So we'll narrow our focus to southwestern Montana. Southwest Montana has seen sustained human population growth for the past decade. In particular, the town of Bozeman has grown 33.7% according to the last census. Residents of Bozeman in general use several highways to access a variety of outdoor recreational activities, Yellowstone National Park being one of those. US 89, pictured to the right, is one of the most popular routes for tourists, as well as residents of the town of Bozeman to access Yellowstone. And the stretch of Highway 89 that travels from Livingston to Gardner, Montana, is colloquially known as the Paradise Valley. Here's a picture of Paradise. As you can see, it's flanked by prominent mountain ranges, and it's comprised of a mix of natural and human altered landscapes. Paradise Valley is also commonly referred to as the gateway to Yellowstone. You can find a lot of the same species in Yellowstone along the Highway 89 corridor. The increase of traffic on Highway 89 and the threat of hitting wildlife while driving through Paradise led me to choose Highway 89 as my study area for my capstone project. And due to the damage that elk can cause and due to the data availability, I focused solely on elk when asking my research questions. So my objectives were to identify a potential location for wildlife crossing structures within my study area. However, in order to answer that, I wanted to know two things. I wanted to know how are elk moving throughout my study area and when are they crossing Highway 89? And what land cover types do they prefer within my study area? So the first objective, identify where they're regularly crossing Highway 89. Here's a small subset of the elk GPS data that I received from Montana Fish, Wildlife, and Parks. Each point here represents an individual elk at one point in time, and the GPS collars record locations at a regular 1 hour intervals the whole time that it's attached to an animal. Through my data sharing agreement with Fish, Wildlife, Parks, I received elk locations from 5 different herds from 2009 to 2020 within my study area. So how does this help me determine where they're crossing the highway? Well, if you pull out one individual from the herd and connect the dots sequentially through time, you can end up with a generalized path of travel. So I connected the dots for each individual in each herd in my study area, and I created a new point layer documenting any time the travel path crossed Highway 89. This is represented by these orange X's here. I also plotted elk carcass data that was collected by the Department of Transportation and Highway Patrol to supplement the crossing data, because in my mind, carcasses are merely failed crossing attempts. Here's what the elk crossing and elk carcass data looks like for my entire study area. And from this view, you can see that there appears to be some common areas where they're regularly crossing and also regularly getting hit. Here's what that same data looks like with a point density map. And by looking at the data in this way, you can definitely pick out a couple of troubling spots that might benefit from a crossing structure. Now, Examining the point data obviously provides valuable information, and past studies have used this type of data to solely inform decision makers where to place their wildlife crossing structures. However, in addition to identifying hotspot areas, I wanted to take a slightly different approach to the problem. I wanted to estimate where elk might cross Highway 89 based on their preference of land cover. The thought being, if preferred land cover types occur on opposite sides of the highway, it's fair to assume that the elk might try to cross the highway at some point. So that's essentially what I did. I connected the preferred land cover types with the least cost path through a variety of different analyses, which I'll get into later. And I consider wherever this least cost path crosses the highway as a potential location for highway crossing structures. So I'll quickly walk you through this process in more detail. The first step was to find imagery to classify. So I gathered up NAPE imagery for the years that you can see here. And I used NAPE because it's the highest resolution, most readily available, and standardized type of imagery that spanned all the years that I had elk data for. And you can see the full extent of each year's imagery here. Next, I performed a supervised object-based classification for each of those 4 years using eCognition Developer. I used a combination of multi-resolution and quad tree segmentations to get the desired segmentation results that delineated objects to the detail that I needed. Here are a couple more examples of the landscape that has been segmented. You can see the Yellowstone and most of the agricultural fields are very nicely delineated in these images. Once the segmentation was complete, I used a rule set that I built based on the observed characteristics of certain objects. Each object, like this lake here, or the agricultural field, or the forest stand that I've delineated, have certain spectral attributes. And this is what I was able to use to discern between and classify certain objects, which is what the result is right here. The end product was land cover classifications for the years 2009, 15, 17, and 19. And each year is divided up and classified into 9 different land cover types, which you can see in the key. And while I'm covering the segmentation and classification stages very quickly, they're what took the most of my time during this project. But it was really crucial that these classifications were as accurate as possible, since the rest of my analyses could be influenced by errors in the classification. So great, we have land cover classes for all 4 years. Next, I wanted to know if elk were selecting for any one of the classes more than the others. So I performed a habitat selection analysis for all 4 years, and I did this by plotting the observed elk points and a random set of points and comparing how many were in each land cover class. The random points here are what you would expect to see if elk were selecting for land classes without preference. And without crunching any numbers, you can clearly see that elk are congregating in some areas more than you would expect if they were choosing land cover at random. Here's a table for the point data from 2015, and you can see here that the agricultural class in this example was selected for at a rate that's greater than what you would expect at random. And similarly, you can see how the selection for water is still much lower than expected, given random points. And this makes sense, seeing as elk probably aren't hanging around floating in the middle of water bodies regularly, right? In the end, 3 out of the 4 years, the agricultural class was the most highly selected for category, and it was followed closely by mixed grassland and shrubland. So using the habitat selection results, I could model the difficulty of traversing the landscape for elk based on their preference or different land cover types. And this was accomplished by combining the habitat preference raster with a slope raster for my entire study area. And the resulting cost raster is a digital model of how difficult it is to move across the landscape with habitat preference and terrain in mind. The easiest route would be one along the green pixels, as those correspond to the lowest cost. And this cost raster is what I used in my cost connectivity analysis. The cost connectivity analysis is just a tool in ArcGIS Pro that does, all it does is connect the different polygons with a least cost path line. The results look like this example here, and where I've created a least cost path between all the most preferred habitat patches. In this example, it's agriculture, because for 3 out of the 4 years, it was agriculture. The final step I took was finding where this least cost path intersected with Highway 89. And I created a new point layer where they intersected, and I'm calling these my modeled crossing points. You can see in the pink X's. So I compared each of the modeled crossing points against my observed elk crossings and observed elk carcass locations. And I did so using incrementally larger and larger buffer sizes around each modeled crossing point. In this picture, you can see 3 of my modeled crossing points represented by the pink X's and their corresponding buffers. I just used half-mile and full-mile buffers here to keep it kind of cleaner. And as you can see in 2015, a majority of the observed crossing and carcass points are within a half mile of my modeled crossing points, and a large majority are within a full mile buffer. On average, between all 4 years, the data is similar. The majority of the crossings and carcass points are within a half mile of my modeled crossings. And that's to say that the real world data is reflected by my crossing points, my modeled crossing points, fairly well. The last step I took was select which of my modeled points seem to have the most potential to aid elk in crossing Highway 89. So I pulled out these 3 modeled crossing points that overlapped with the most observed crossings and most observed points, carcass points. And these 3 locations are what I'm recommending for my potential crossing structures in my final report. Here they are set against the point density map. And as you can see, they do correspond with some of the hotspots in observed wildlife crossing activity. Now, before I conclude, I just wanted to stress that there's a lot of things to consider when citing some of these crossing structures. For example, one thing I didn't have time to touch on was the issue of land ownership. Much of Paradise is privately owned, and of the 3 crossing structure locations that I recommended, they're all adjacent to private property. So if these structures were built, then private landowners would likely need to be reimbursed for land taken from them. There is, however, public land strewn about the valley, and that could be an easier and more popular alternative to building structures on privately owned land. Here you can see that it wouldn't be too large of a move to relocate this one crossing structure recommendation either north or south to be adjacent with public land. And while I believe my analyses have yielded some viable locations, it's just one small piece of the puzzle. And the land ownership issue is just one of the plethora of other things to consider before any decisions are made. So I'd like to thank the Montana Fish, Wildlife, and Parks for supplying the elk GPS collar data, as well as the previous wildlife crossing studies that they've conducted. Thank you to the Montana Department of Transportation and Highway Patrol for supplying the elk carcass data. I'd like to thank my supervisors at Maxar, who graciously allowed me to use some of our elevational products for academic use. My land classifications really wouldn't have been possible without those. And finally, thank you to my graduate advisor at Penn State, Dr. Fritz Kessler, for all the guidance and thoughtful conversations that we had. With that, thank you for taking the time to watch my presentation, and I'm happy to answer any questions y'all might have.